Transition metals flashcards. I'm gonna try to make this as quickly as possible. This video, so just like basically speed running through these flashcards. This is the first time in a while I've gone through these flashcards, so I'm not gonna remember any of this, a lot of it, but that's fine because the whole point. I'll tell you the plan for this channel because obviously I'm posting on this channel. Today, obviously, it's Friday. Finish off this. Then that means then tomorrow go through all the flashcards for chemistry paper 1. Get out of the way. Obviously all the equations and the practicals. Get out of the way. And then I'm going to revise the rest of the day for psychology. And then the past paper questions I will also go through, but I'm going to print off all the past paper questions for paper 1 for chemistry and then go through that. So I'm about to have to wake up pretty early to do all of that. Same thing with Sunday. No, yes, but Sunday I'm just going to do a bit more psychology. Monday's my psychology exam. Get out of the way. And then chemistry. I finish in the morning for psychology. So then I've got like a good 8 hours to revise for chemistry. Then go sleep, wake up, another 2. And in the morning of the exam, I would just be going through flashcards and practicals and equations. Anyway, the formula of delta E, the size of the energy gap. Delta E equals HV, which equals HC over lambda. You do need to know that. Where V is the frequency of light absorbed, H is Planck's constant, C is the speed of light, and delta is the wavelength of light absorbed. Delta equals HV, which is HC over delta, or lambda. Where's the D block found? In the middle of the periodic table, most transition elements from titanium to copper. Okay, obviously it's in the middle of the periodic table. I never asked you that one. What? Transition metal, a metal that can form one or more stable ions with a partially filled D subshell. 2 things that happens when transition metals form positive ions. S electrons are removed first, D electrons are removed second. What do transition metals form? Transition metals form at least one ion that has between 1 to 9 electron d orbital. Again, that's not really a great flashcard. Only 2 non-transition metals of period 4 are scandium and zinc, and they can contain, a d orbital can contain up to 10 electrons, so scandium and zinc. Incomplete d subshell causes special chemical properties which are only applicable to transition metals. Scandium zinc, which I just said, are 2 non-transition metals in D block. Why? Because scandium forms Sc3 plus only, empty D sublevel. Scandium has an electron configuration of 3d14s2, loses 3 electrons, has an electron configuration as argon. Zinc only forms Zn2 plus. Zinc has electron configuration argon 3d10-4s2, loses 2 electrons, forms a full 3d sublevel. 3 key characteristics of transition metals, you just need to spot these. All have a high density, high melting point. Ionic radii are more or less the same. Again, I don't think that's relevant to spec. The ones that I don't think are, I'll double check obviously, then I'll get rid of them if they aren't. 3 chemical properties of transition metals can form complex ions, form coloured ions, good catalysts. Complex ions, coloured ions, good catalysts. The colours refer to the aqueous ions, and oxidation states in transition metals can exist in variable oxidation states. States the colours of all of these. Okay, so MnO4 minus is purple, Cr2O72 minus is orange, VO2 plus is yellow, VO2 plus is blue, V3 plus is green, V2 plus is violet, Mn2 plus is pale pink, Fe2 plus is pale green. State the colours of the cobalt ion. The cobalt ion is obviously pink, the nickel ion is obviously green, and the copper ion is obviously blue. So some of them are like, you already know. 2 special ions and the colours depending on conditions. So you've got Cr3 plus, when surrounded by 6 water ligands, is actually violet, but when water ligands are substituted, Cr3 plus is green. Fe3 plus, surrounded by 6 water ligands, is purple. Solution appears yellow though due to hydrolysis. Transition metals show variable oxidation state because the energy levels of 4s 3d sublevels are very close to each other. Different number of electrons are gained/lost using similar amounts of energy. Again, I don't think that's part of the spec. Complex is a central metal atom/ion surrounded by coordinately bonded ligands. That's a complex. Ligand, a species that donates a pair of electrons to a central transition metal/ion to form a coordinate bond. Donates a pair of electrons to a central metal atom to form a coordinate bond. Coordination number, a number of coordinate bonds that are formed with the central metal. A key fact about ligands don't have to be all the same. Obviously. Because obviously with the reaction of metal aqueous ions with you have them with the Cl minus ligands and NH3 plus ligands. With the smaller ligands and bigger ligands, obviously you don't have to be all the same. Color of CuCl42 minus and color of that. So color of CuCl42 minus is yellow. Color of CoCl42 minus is blue. 4 coordinate bonds can form a tetrahedral square planar shape. Silver complexes in terms of coordinate bonds. Some silver complexes with 2 coordinate bonds. The overall charge on the complex ion equals the total oxidation state. Hexacoordinated, 6 lone pairs are donated to form 6 coordinate bonds in an octahedral structure. Monodentate ligands that can only form 1 coordinate bonds. Multident ligands that can form more than 1 coordinate bond. And ethanediol ion is C2O42 minus. Bidentate ligands, multidentate ligands that can form 2 coordinate bonds. A key fact about ligands in terms of lone pairs of electrons to form coordinate bonds: ligands must have at least 1 lone pair of electrons or can't form coordinate bonds, which makes sense because ligand is an electron pair donor. Hemoglobin protein, a protein found in blood helping transport oxygen around the body. 5 characteristics of hemoglobin. Fe2 plus ions, which are hexacoordinated. 4 coordinate bonds come from single multidate ligands. 4 nitrogen atoms come from the same molecule coordinate around the Fe2 plus. The other 2 coordinate bonds come from globin oxygen and a complex transport oxygen to where needed, therefore swap for H2O. When oxygen concentration is high in the lungs, oxygen molecules substitute water ligands and bonds coordinately to Fe2 plus ions to form oxyhemoglobin. And when oxygen is needed, exchange for water molecules, hemoglobin returns to the lungs, the process restarts. If carbon monoxide is inhaled, hemoglobin swaps a water ligand for carbon monoxide. It forms carboxyhemoglobin, and carbon monoxide is a strong ligand, therefore does not react readily with oxygen. Hemoglobin therefore can't transport oxygen. Carbon monoxide poisoning starves the organs of oxygen, causing headaches/unconsciousness. Example of complex ions through optical isomerism: octahedral complexes when 3 bidentate ligands, ethane 1,2-diamine, coordinate bond with central metal ion nickel. Complex ions show optical isomerism and consist of 2 forms that are non-superposable images. Cis trans isomers, they can form in octahedral or square planar complexes. A specific kind of octahedral complex known as cis trans. Octahedral complexes 4 monodentate ligands of one type, 2 monodentate ligands of another type. 2 odd ligands are opposite each other, it's trans isomer. If they're next to each other, it's cis isomer. Square planar complex ions, so cis/trans isomer, have 2 pairs of ligands, so that. Cisplatin, what is cisplatin? Cisplatin is a complex of platinum 2 with 2 chloride ions and 2 ammonia molecules in square planar shape. Ligands, they split the 3D sublevel into 2 energy levels. When ligands bond to the ion, some orbitals gain energy, splitting the 3 orbitals into 2 energy levels. How do electrons occupy high orbitals? Need energy equal to the energy gap, delta E. We get it from visible light. 4 factors affecting delta E, size of energy gap: central metal ion, oxidation state, ligands, and coordination number. Electrons tend to occupy lower orbitals, the ground state, and 3p orbitals all have the same energy. The formula to find the oxidation state of metal ion, oxidation state of metal ion, equals total oxidation state minus sum oxidation state of ligands. The colors of compounds in terms of absorption, the colors of compounds are the complement of those absorbed. Delta E is the size of energy gap. Visible light hits the transition metal. The frequency absorbed when electrons jump up to higher orbitals. The rest of the frequencies are transmitted and they combine to make complement of colors of that. When no 3D electrons in terms of color, no electron will jump, no energy absorbed, compound will look white/colorless as no energy absorbed. A change in coordination number always involves a change of ligand, and a change in ligand causes a color change even if the oxidation state and coordination number remains the same. Ligand substitution: 1 ligand can be swapped for another, causing a color change. If ligands of similar size charge, coordination number of complex ions doesn't change, neither does the shape. But if the ligands of different size charge, the coordination number of complex ions does change, so does the shape. Example of ligand exchange reactions: hydroxide precipitate form and small sodium hydroxide solutions are added to metal ions. Hydroxide precipitate sometimes dissolves. What do different ligands form in terms of bonds? Different ligands form different strength bonds. Delta H is very small in ligand exchange reaction. Two characteristic ligand substitution reactions can be easily reversed unless new complex ion is much more stable than the other one. Exactly. When is it hard to remove? When the new ligands form stronger bonds with central metal ion than the old ligands. Multidentate ligands are hard to remove because they form more stable complexes than monodentate ligands, and the positive entropy change makes it a more stable complex. Coordinate bonds in ligand exchange reaction are broken formed, and strength of bonds is similar to strength of new bonds formed. Chelate effect in terms of ligands. Chelate effect basically explains why multidentate ligands always form more stable complexes than monodentate ligands. Why is it difficult to reverse between ligand exchange reaction? Reverse them called the decrease in entropy, and chelate effect is basically increase in stability. Why is delta G is negative in ligand exchange reaction? Delta H is almost zero, delta S is big and positive, therefore delta G is negative, therefore reaction is feasible. For oxidation state, vanadium exists in solution of the colors V2 plus aqueous violet, V3 plus aqueous green, VO2 plus blue, VO2 plus equals yellow. So V2 plus violet, V3 plus green, VO2 plus blue, VO2 plus yellow. Name for this vanadium ion, vanadate ion. And how can vanadium ions be reduced? By adding them to zinc metal in acidic solution. What happens when a monodentate ligand substitute with multidentate ligands? The number of particles in solution increases, more particles, greater entropy, more likely to occur. Redox potential tells you how easily it is reduced to a low oxidation state. Larger redox potentials, less stable ion, more likely to be reduced. What? So redox potentials tells you how easy it is to reduce to a low oxidation state. Then I said two key facts about larger redox potentials. More likely to be reduced. Obviously it's going to be less stable because it tells you how easy it is reduced. So if it's a higher number, it's more likely to be reduced. Yeah, some of these flashcards are not great, unfortunately. Sorry, I made these. I was using the textbook. But yeah, measurements of standard electrode potentials are measured with reactance concentration 1 mole per minus cube against a standard hydrogen electrode at 298 Kelvin and 100 kilopascals. You need to know that. Standard electrode potentials are measured against a standard hydrogen electrode, and redox potentials are larger in a acidic solution as the ion is more easily reduced. Aqueous ions at standard electrode potential. Any aqueous ions are surrounded by water ligands, and different ligands make redox potentials because the larger or smaller depending on how well they bind to metal ion in particular oxidation state. Ions need to be reduced and release when reduced. To need H plus ions to reduce and release OH minus ions when reduced. Tolerance region contains silver complex and silver transition metal found this easily reduced to silver metal. Describe how to make tolerance region. Adding enough ammonia to silver nitrate solution from colorless solution containing complex ions AgNO3 2+. Transition metals are good catalysts because they change oxidation state by gaining / losing electrons in d orbitals, transfer electrons to speed reactions. Two equations of the contact process: V2O5 plus SO2 to form V2O4 plus SO3, V2O4 plus half O2 to form V2O5, V2O5 plus SO2 to form V2O4 plus a half O2, V2O4 plus a half O2 to form V2O5. V2O5 plus SO2 to form V2O4 plus SO3, V2O4 plus a half O2 to form V2O5. You need to know those equations. Perfect. And the catalyst used is a heterogeneous catalyst. Vanadium 5 oxide is able to oxidize this to this because it is a strong enough, because it can be reduced to this. And name of this is ethanediol ions. Heterogeneous catalysts or catalysts are in a different phase from the reactants, in a different physical state. Heterogeneous catalysts work by reactions happen at active sites located on the surface, increasing surface area of catalyst, increasing number of molecules at the same time. Two uses of support mediums makes the area of catalyst as large as possible, and therefore only a small coating of catalyst to provide a large surface area, minimizing the costs. So provides us large surface area, minimizing costs. Two examples of heterogeneous catalysts: iron in the Haber process, nitrogen plus 3H2 to form 2NH3, and vanadium oxide in contact process with the V2O4 plus alpha 2 to form V2O5, V2O4 plus, I just went through it. Catalyst poisoning: impurities in reaction mixture binds to catalyst surfaces, blocking the reactants from being absorbed. Three disadvantages of catalyst poisoning: reduce surface area catalysts available to reactants, slowing the rate of reaction, increases the cost of chemical processes, less product maintained over a certain time, catalyst needs replacing. Sulfur ions poison ion catalyst Haber process. Hydrogen produced from methane obtained from natural gas containing impurities, only sulfur, any sulfur not removed, absorbed. An iron from sulfide, therefore stops iron from catalyzing efficiently. Homogeneous catalysts, obviously, all in the same physical state as the reactants. Condition for homogeneous catalysts: aqueous catalyst for reaction between two aqueous solutions. Homogeneous catalysts work by combining with the reactants from intermediate species, which reacts to form products and reform catalysts. Again, I don't think you need to know that. Why catalyst carries on catalyzing reaction? Because catalyst already forms on two humps in the profile for homogeneous catalyst respond to two steps in reaction. Again, I don't know. I don't think you need to know that. I think these are just useless flashcards. The ion that catalyzes this, you do need to know this. The Fe2 plus ions, and both ions negative charge and repel each other, won't collide, high activation energy. Kind of catalyst: it is a homogeneous catalyst, same for its reactants, and it speed syncs up because the reaction involves positive and negative ions. Unfortunately, I didn't write down the equations of the flashcards, which is kind of dumb. But instead, I've got them all in a sheet, which I'll be going through for the next couple of days, and inshallah, I will memorize all of them. Name of this is peroxo disulfate, and autocatalysis is when a product catalyzes a reaction. Example of homogeneous catalyst is Mn2 plus, is a reaction between C2O4 and MnO4 minus, and as reaction progresses in autocatalysis, where autocatalysis is when a product catalyzes the reaction, is that the amount of product increases, therefore reaction speeds up. When transition metal compounds dissolve in water, then water molecules form coordinate bonds with metal ions, forming metal aqueous complex ions. Water molecules form coordinate bonds by donating a non-bonding pair of electrons from oxygen. Water molecules are neutral. Acidity reactions: solution containing metal aqueous 2 plus ions, reaction between metal aqueous and water. 3 plus aqueous ions form more acidic solutions because they're small but big charge, high charge density, more polarizing, attracts electrons, weakening OH bond, more likely H plus ions to reduce, more acidic. More positive ion means more polarizing power. Adding hydroxides produce insoluble metal hydroxides. Why do only two steps of metal equal 2 plus ions? Only two water ligands need to be deprotonated to make 2 plus 2 complex uncharged, therefore insoluble. Again, I don't need to know. What do metal hydroxide precipitate do? They dissolve an acid, act as a Bond-Lowry base, except the H plus ions. What do metal 2 plus ions form in the reaction with sodium carbonate? Form insoluble metal carbonates. Aluminium hydroxide is amphoteric. You should know that from properties appears to the elements in the oxide. What do metal 3 plus ions form when reacting with sodium carbonate? Stronger acid source, higher this in solution. Carbonate ions react with this, remove solution, shifting equilibrium to right instead of displacing water from metal ions. Obviously, that was like the first recap. Like with the other ones, thermodynamics, obviously I've been through those time. But transition metals, like honestly, and this is the biggest topic in paper 1. So yeah, it's calm because we're gonna go for again tomorrow, and then tomorrow, and then tomorrow, and then tomorrow. And that's that reinforcement. It should be perfectly fine.